Hello students, welcome back. Today we're going to be doing the basic algebra, exponents, radicals, polynomials, and special products. This is the playlist for the college algebra for the UC system. And alright, let's get started. So, today we're going to be starting first with the basic algebra, operations specifically. So, what can we do here? Let's take a look at the following. Here we have the operations, the algebraic operations. So we have commutative property. A plus B is equal to B plus A. Here, A and B are real numbers. Right, last time we covered the real numbers and their application and ordering. And today we're going to be actually doing operations with the real numbers. Okay, besides A and B, we often in algebra use X. Right, so an example would be, examples here would be the following. 4x plus x squared is equal to x squared plus 4x. Right, so the order of addition is commutative, meaning that it doesn't matter if you add first 4x and then x squared, or x squared and then 4x. All right, then the second one is going to be the property of multiplication. AB is equal to BA, so A times B is equal to B times A. And essentially, we can say 4 minus x times x squared is equal to x squared times 4 minus x. All right, so multiplication sign, oftentimes in mathematics, we write it as a dot. Sometimes it can be written as little x, depending on the book you're reading. But most of the time, it's just going to be either empty space or a little dot, which would indicate that it is multiplication. The next property is going to be associativity property. So associative property, and that means if we have a parenthesis, which indicates the order of operation, right? So parentheses are going to be always first. So we're always caring about the parentheses first and then the rest of the things. So if we first add A plus B and then add C, it will be the same thing as first adding B plus C and then adding A. Right? Similarly, with multiplication, we can first multiply A and B and then multiply by C. Or we can have B and C multiplied first and then multiply by A. So let's take a look at this. We can I'll also add A, B, and C. Okay. Then we also have distributive property. So the way the distributive property works is we have B plus C in the parenthesis and we're multiplying it by A. The rule is we're going to be multiplying with the arrows, so A times B plus, because we're going over the plus sign, right? And it's going to be A times C. So the final answer here is going to be A times B plus A times C. So an example of that would be x times 4 plus 7x, which is equal to, so x times 4 is going to be 4x, plus 7 times x times x. So x times x, we're going to learn it in a bit, but that would be 7x squared. We're going to be learning today the exponentials and the rules for exponentials. Okay, next one is going to be the additive identity. So identity meaning that if we use that operation, it's not going to change anything. So in addition and in algebra, one of the identities is additive identity 0. Right? So if we add 0 to any number, nothing really changes. A plus 0 is equal to A. Multiplicative identity. So if it's multiplication identity, right? If we multiply any number by 1, that number is not going to change. So A times 1 is equal to A. So for example, 5 times 1 is going to be equal to 5, right? Or any other number times 1 is going to be that number. Then we also have inverses. So additive inverse property is when we have, so if we have positive number A, we also have a negative number A, because when we add them together, we're going to get a 0, right? We're always going to get the additive identity. And then we also have multiplication identity. So multiplicative identity would be, inverse property would be, we have to multiply two numbers to get a 1, right? So if A is non-zero, this is the important part, if A is non-zero, then we can have a fraction which has in the denominator our number. So A times 1 over A, we essentially have A divided by A. That's only one way we can do it, so the answer is 1. Okay, so these are the basic algebra rules. Now, we can also have the sign, the properties of negation and equality. So let's take a look at the following problems. So, the next part would be this. The following properties. So if we multiply negative 1 times A, where A is the real number, we're going to get negative A. Right, an example of such would be negative 1 times 5, which is equal to negative 5. Okay, and then negative times negative, so negative 1 times negative 5, that will give us positive. So negative number times negative number will always give us positive number, right? The negative number times positive number will be giving us negative number. And we can translate the negative sign from one number to another if we're multiplying. And then once again, if we're multiplying two negative numbers, we will end up positive. And here's distributive property, right? From the last few minutes ago, we were doing the distribution properties. So this one is one of them. We can think of it essentially as negative 1 times a plus b. And if we apply the distributive property, we're going to get negative a minus plus negative b, right? But negative is always a dominant one, so we're going to have negative a minus b. Okay, if a is equal to b, then if we can add and subtract a number c, right? So we can, if we are adding a number to a, we must add number to b, right? So if we have x plus 2 is equal to 7, as an example, right? If we decide to subtract 2 from both sides, so we decide to subtract 2, we have to do it from both sides. So negative 2 and negative 2. So essentially, right, we're going to write it like this. It's going to be x plus 2 minus 2 is equal to 7 minus 2. And why did we do that? We did that to get a zero identity, to get a 0 here, right? Because positive 2 minus 2 is going to give us a 0. And x plus 0 is just x. So x is equal to what? 7 minus 2 is going to be equal to 5. Right? So we know that x is equal to 5. Okay? And we could do the same thing, adding the numbers. And then if, the next property, if a is equal to b, then a times c is equal to b times c. As long as c is not equal to 0. And same thing with a and b. Right? Because we cannot divide by a and b. If it's 0, we cannot divide by 0. Very important property. And then if, so this one is the opposite one, right? It's 6 and 8 are tied together. Okay. And then the 9th one is if a times c is equal to b times c, then a is equal to b, right? So this is also an important condition. Here we can kind of avoid this in this one, but still have to keep that in mind every time we're working with it, but have to be careful not to divide by 0. Okay. So this would be property of negation. Now, since we've been talking a lot about 0, let's take a look at the 0 property. And we're going to take the properties of 0. Okay, so let a and b be real numbers, variables, or algebraic expressions. So number 1, if we add a 0, essentially additive identity, we're just going to end up with our number. And same thing if we subtract the additive identity, it doesn't change anything. Okay? And for number 2, if we multiply by 0, any number multiplied by 0 will give us 0. Okay, that's pretty straightforward. If we divide 0 by any number, we're still going to be 0 as long as a is not equal to 0, because 0 over 0 is not defined, right? Undefined, we do not know what it's that. All right, we cannot do that. This is not defined operation. And for number 4, we cannot divide by 0. In algebra, we never divide by 0. So we also have a 0 factor property. So if a times b is equal to 0, then either a is equal to 0 or b is equal to 0. Right? And why is it useful? So through that property, we can later on solve equations. Solve equations, which we will talk in a bit in the upcoming lessons. Okay. And one of the very important part of algebra is the properties of operations and fractions. So let's take a look at this. Take a look at the following properties. F. Okay. So it's going to be the fraction properties. Let a, b, c, and d be real numbers, variables or algebraic expressions, such that b and d are not equal to 0. This is very important. We always have to keep that in mind, especially when we're dealing with equations. Okay, so equivalent fractions. So it's the fractions which are equal. They are equal if and only if A times D is equal to B times C. So an example would be 1 over 2 is equal to 2 over 4. Right? Why? Because if we cross multiply, 1 times 4 is equal to 2 times 2. And that will equal to 4. So that's true. So this is an equivalent fraction. Rule of signs. So if we have a negative sign in front of the fraction, we can move it in the numerator, right? So the top of a fraction is called numerator. So if we have A over B, this is going to be numerator, and the bottom is going to be denominator. Okay, so if we have a negative sign, we can either move it to the numerator or to the denominator. And if we have negative sign in both numerator and denominator, and we could factor it out, then the negative sign is going to cancel out and the fraction is going to remain positive. And we can also generate equivalent fractions, as we saw in the first example. So A over B is equal to A times C over B times C, where C is not equal to 0, right? So we can multiply by a coefficient. So what would be an example? Let's say C is equal to 5, then 1 times 5 is 5, and 2 times 5 is 10. So 5 over 10, that's also 1/2. Right, perfect example. So if we subtract and add fractions, right, we have to make sure that we always have the same denominator. Right, so if we have the same denominator, the rule would be that the denominator stays the same, and we would only deal with numerators. And then if the denominator is not the same, first we gotta find a common denominator, which is, if we have a denominator B and D, our common denominator is going to be multiplication of B times D. And then how would we deal with it is, well, B times D, we have to take it to the side and have a B times D. So for the first part, we have to divide it by the first denominator, which is B. So our multiplier is going to be D. Okay, so we're going to have A times D over BD. And then for the second part, we'll have BD over the second denominator, which is D, which is going to be giving us multiplier of B. So we're going to have C times B over BD. And now we can add or subtract, and we can use number 4 to add and subtract, which will give us A times D plus or minus C times B divided by B times D. Okay, and then if we multiply fractions, we're directly multiplying numerators and denominators. And if we have any common terms that we might be canceling out, right, like a multiplicative inverse, right, we can simplify. And then the last part is to divide fractions. So if we divide fractions, this is one way to write it, or we can write it as A over B divided by C over D. Right? This is a very tall fraction, but essentially we would have to take the bottom fraction, define it, right? This is the bottom fraction, C over D, and we would flip it. So we would have A over B times D is now our numerator, C is our denominator. Right? And that's useful in one of the specific examples when we have 1 over, let's say, A over B. Right, it's a triple fraction. It's a common thing in algebra. So how would we resolve it? It would be just B over A. All right, perfect. So we're essentially done with fractions, and now let's go ahead and move on to exponentials. Right, we're going to talk about exponentials and powers. I already introduced it for the x variables, but now we're going to be introducing it in general. So the definition of exponents. Definition of exponents. So if a is a real number and n is a positive integer, then a to the power of n is equal to a times a, etc., n times, right? So a factor of n. Okay, and where n is the exponent and a is the base, you read a to the n as a to the power to the nth power, right? So if you have a square, that means a to the second power. Or if you have the third power, we're going to have a to the third power, or a cubed, right? We can have a square and a cubed. And then the rest of the powers are going to be based on the number we have. Okay, now let's take a look at actually properties and some examples of the exponents. So here would be an example. and properties. So once again, let a and b be real numbers, variables, all algebraic expressions, and let m and n be the integers. All denominators and bases are non-zero. This is very important. This is very important. So, few of the properties of the exponent. We will have that property number one, if we're multiplying two numbers with the same base, right? Same base, notice. A is the base. So if we have the same base, we're going to have a to the power of m times a to the power of n. That's going to be the same thing as a to the power of m plus n. So if we have, let's say, x to the power of 1, or just, we usually write just x, times x to the power of 3, that would be x to the power of 1 plus 3 is equal to x to the power of 4. And that works actually with any fraction. Any fraction including any numbers including fractions and negative numbers and irrational numbers and any powers of real numbers that will work with. Okay, perfect. So number two is, well, when we divide two numbers with the same base, we are subtracting the power, right? We are subtracting the power. This is the most common thing in algebra to remember. A lot of students make mistakes in that. So we have to subtract the powers. And if, let's say, we had a negative power, then negative gives us positive, right? So we also have to keep that in mind. And 2 and 3 are tied together, right? Because a to the negative n is exactly the same thing as 1 over a to the n, because this is where it's coming from, right? Because we can rewrite a to the m over a to the n is equal to a to the m times a to the negative n. And then by rule number 1, we're going to have a to the m plus negative n, which is equal to a to the m minus n. All right. Then number 4, any non-zero number to the power of 0 will lead us to 1, always. So, and how we can check it, so a over a, that's the same thing as a to the 1 minus 1, which is equal to a to the 0, but we know that a over a is equal to 1. And that's going to work for any power m over m, right? For any power, it doesn't have to be 1. Then we also have distribution law, right, of the powers. So if we have a times b in parentheses in its multiplication, this is very important because a plus b in parentheses is not going to be the same thing. So a times b to the power of m is equal to a to the power of n times b to the power of n. And here would be a corresponding example for it. And then a to the power of m to the power of n, the power is going to get multiplied, so there is no addition. So we have a to the power of m n times, right? Essentially, a to the power of n to the power of n, that's going to be a to the power of m times a to the power of m times n times a to the power of m, right? N times. So it's going to be a to the power of n times m. Very important. And then number 7, similar idea. We can multiply a over b m times, and that's going to be a to the power of m over b to the power of m. Here, specifically for the square, right? Square will always make things positive because square makes two numbers multiply each other. And if we multiply two negative numbers, we're going to always get a positive number. So number 8 gives us that the absolute value of a squared is the same thing as absolute value squared, which is the same thing as a squared. So second power cancels out essentially the absolute value. But how about roots, right? Can we actually define roots? And what is a root? And can we have a proper definition of it and how it looks like? Yes, we can. So we're going to talk about fractional exponents. Or we can also call them roots. Okay. So those kind of things we'll have in the following definition. So let a and b be real numbers, and let n be a positive integer, where n is greater or equal to 2. If a is equal to b to the power of n, then b is the nth root of a. Right, this is going to be the nth root of a, and specific cases, if n is equal to 2, then the root is a square root. Right, and how would we write a square root? A square root, it would be so either 1 to the power, so a to the power of 1 over 2, or it's the same thing as square root of a. And then if n is equal to 3, we're going to have a cube root, which would be a to the power of 1 over 3, or the same thing as cube root of a. Okay, and one of the very important roots that we might have in algebra is called the principal root, right? And the principal root is a very special property of a square root. So let a, and not only square root, but one of them is. So let a be a real number that has at least one nth root. The principal nth root of a is the nth root that has the same sign as a, and that is denoted by a radical symbol, right? We call the square root as a radical, right? This symbol right here, specifically radical, it's going to look like this. This is the radical. And here we would have a number n. That's the nth root. So the number n is the index of radical, and the number a is the radicand. But we can call it also a base. So when n is equal to 2, omit the this and write this instead of this, right? So oftentimes people omit the 2 because this is just implying that this is a square root. Okay, and so when we are dealing with a square root, right? If we have a positive square root of 4, that's going to be 2. We have negative square root of 4 is equal to negative 2, right? And when we are solving equations, the square root sign most of the time implies positive root. But in equations, sometimes when you have x, let's say we have an unknown variable x to square power, right? Something squared, something times something is going to be equal to 4. So if we say that x is equal to square root of 4, it's not quite right, right? Because it only gives us positive 2. But we know that there might be another solution. So we're going to say plus or minus square root of 4, which will give us plus or minus 2. So it can be either plus or minus, because if x is minus, negative 2 times negative 2 is going to give us 4. And 2 times 2 will also give us 4. So we might have multiple variations. We will always have to keep that in mind. And of course, we might have a certain generalization table, right? If we have a generalization for the square roots and the cube roots, so let's take a look, and just in general, the nth root. So this table is going to be useful for it. So the generalization about the nth root of real numbers. So if a real number a is positive, n is even, the root's going to be the following. Okay, and that would be an example. If a is greater than 0 or less than 0, but n is odd, we can still take the cube root, right? We cannot take, as we'll see, we will not be able to take a square root or any even root if a is less than 0. It's not a real number. It does not belong to real numbers. So there is no real solution. But if a is equal to 0, then it will always be 0. Okay, and now let's actually take a look at some examples and some properties of the radicals. Just as previously, we're going to have the following table. So let a and b be real numbers, variables or algebraic expressions, such that their indicated roots are real numbers, and let m and n be positive integers. So properties. If we have nth root of a to the power of m, it's the same thing as nth root of a to the power of m, or we can also write it as a to the power of 1 over n to the power of m, and then by using the property of powers, it's going to be the same thing as a to the power of m over n, so that is a fractional power. Then if we multiply two radicals with different bases but the same power of radical, we can bring it under the same radical. Same thing with division. If we have this is essentially, we can think of it as a to the power of 1 over n to the power of 1 over m, so that's going to be a to the power of 1 over n times m, right? By the rules of radicals and powers and fractions, right? And then nth root to the power of n, we can rewrite it as a to the power of 1 over n to the power of n, which is equal to a to the power of n over n, which is equal to a to the power of 1, which is a. And if we have for n even, we're going to have an absolute value because it can be positive or negative. But for odd, it will always be positive. All right. So now we can also essentially call this called a rational, right? This is a rational exponent. Okay, perfect. And now let's go ahead and take a look at some of the polynomials. Right, we've been mentioning x's and y's and just variables in general, but now let's actually give a definition of polynomial. So definition. So by definition of the polynomial, we'll use the following. Let a naught, a1, and a2 be real numbers, and let n be a non-negative integer. A polynomial in X is an expression of the form a sub n times x to the n plus a sub n minus 1 times x to the n minus 1, etc., all the way to a sub 0, where a sub n is not equal to 0. So we call this a polynomial of degree n, where a sub n is the leading coefficient, and a sub naught is the constant term. Okay, so this is a constant, right? So in front of the x to the n, or in front of every x, we have just a constant term. Okay, so we can have a few examples, right? What would be an example? If we have, let's say, 4x squared minus 5x7 minus 2 plus 3x, this is not a standard form, right? We always have to have a standard form, and the standard form is we are going with the highest degree polynomial, so highest power. So what's our highest power? It's 7, right? So the correct one would be negative 5x to the 7 plus 4x squared plus 3x minus 2, right? So we are matching specifically this form, and every polynomial should be always matching that form. We call it a standard form. Okay, now we can have some of the special products of the polynomials and a few of the examples related to it. So let's take a look. Let u and v be real numbers, variables, or algebraic expressions. Special products, sum and difference of the same terms. So if we have u plus v, u minus v, so we can use the distribution law. So it's going to be u times u, u times negative v. So we're going to have u times u minus u times v, and then v times u minus v times v, so plus v times u minus v times v, right? So we can rewrite it. So it's going to be u squared minus uv plus, we can rearrange it to be uv minus v squared. So clearly these two cancel out, and we're going to have the final answer to be u squared minus v squared, which is exactly what we got here. Okay, and here we can have a more distinct example. Then we can have a square of a binomial, right? Square of a binomial is u plus v squared. So how can we prove it? So it's u plus v times u plus v. So applying the same idea as in the previous example, we're going to have u squared plus u times v plus v times u plus v squared. So if we simplify, we're going to have u squared plus 2uv plus v squared. And then similarly, we can do it for the following. It's going to be u minus v times u minus v, which is equal to u squared minus u times v minus v times u plus v squared, which if we simplify, negative uv minus uv, it's going to be 2uv. So we're going to have u squared minus 2uv plus v squared. And then cube of a binomial, we're going to have u plus v times u plus v times u plus v. And then we can simplify, right? And we will end up with the same expression. Similarly for u minus v. And here we have a few of the examples of how it's actually performed. Okay, so we covered for the special products, and this would be it for this lesson. Thank you, and I'll see you in the next lesson.